In this video, we're going to take a look at measures of center in spread. So in addition to illustrating quantitative data using graphs and charts, we also want to present numerical summaries of the center and spread of the data set. So measures of center, we have two that we're going to look at in this class, the median and the mean. The median is a positional measure of center, and specifically 50% of data values are going to lie above the mean and 50% of values are going to lie below the mean, which makes the median also referred to as the 50th percentile, where percentile is in reference to the percent of values that lie at or below the data value. So for instance, if you are placing at the 70th percentile in a test, then that means 70% of scores were at or below the test score you received. The median does not have a dedicated symbol, unlike the mean. We just write median or MED as a shorthand version of it. And if the data are ordered from smallest to largest, which we must do first of all, the median is going to be the observation right in the middle of the data set. So when there's an even number of observations, there's going to actually be two middle values. In that case, the median will be taken as the average or mean of the middle pair of values. When we have an odd size data set, the median will be the middle data value itself. Okay, so for the mean is also referred to as the arithmetic average. It's usually what we're referencing when somebody says the average of some set of values. And it describes the balancing point or fair share value of a distribution. The sample mean is labeled with Y bar, and it is computed as the sum of all the observations divided by the number of observations. And so here's the formula itself, and you'll see this symbol in a few different places in our course, and that just means sum. So take the sum of all of the Y values, the individual data values, and divide by N, which is reference to the sample size. The population mean, remember, is labeled with the symbol mu, MU, if you wanted to write it out in terms of its name, and is similarly computed as the sum of the observations, but in the whole population, divided by the size of the population. And the size of the population symbol, remember, is uppercase N as opposed to the lowercase n, which is the sample size. So here we're going to take a look at a couple of examples doing the calculations for mean and median by hand. So the mean is a pretty straightforward one. The mean, which we would symbolize as Y bar, we sum the data values, divide by the number of data values. In this case, we add up all our data values. We know that our sample size N is equal to 9, which immediately tells us for our median, given it's an odd sample size, that it will be one of the data values themselves, the one in the middle of our data set. That will be the value of the median. Now the mean, we have to do some calculating. We do not have to order the data first to do the calculation, which is kind of handy. And you're just going to add those values together. So 8 plus 6 plus 7 plus 5 plus 3 plus 0 plus 9 plus 0 plus 0. Divide by the number of values in your data set, which is 9, and then you'll get your mean. Now in this case, it comes to 4.22222 repeating, but the general rule of thumb in class is that you're going to want your mean, so any of the statistics we calculate, to go to one decimal place more than what the data values were in the data set. So this is for quantitative calculations, so things like mean and standard deviation, which we'll go over in a little bit, median as well when you're needing to take an average. Make your decimal placement to one more than your data set it had in, or the data values in your data set. So we'll go to one decimal place here, and we would usually put down our units as specific units, so inches or feet or pounds, whatever it may be. This data set doesn't have specific units given, so we'll just leave as a placeholder units. Okay. Now we want to get to the median. The first step for calculating the median is to order the data from smallest to largest. You do not want to ever forget that step when you're doing this by hand. So the zeros are going to come first, 0, 0, 0, 3, 5, 6, 7, 8, 9 is our data set, and we'll only be going by hand, like doing these calculations by hand with very small data sets. So it's easier just to kind of put your fingers on either of the end values and work your way in one by one to find the middle. And in this case, 5 is going to be in the middle, right? So we have 4 data values on either side of it. That's a good way to double check that you found the middle value. There should be an equal number on either side when we have an odd number in our data set. So the median is that single middle number, and it'll be equal to 5. Again, units here since we don't have specific units given for our data. But in any case, it'll take the same units as the data itself, like the mean. Both of those will have the same units as the data set. Okay, so in this next example, you'll notice that the data that we have is really similar. We still have 9 data values. So n is equal to 9, and everything looks the same except I've changed one of those zeros into a negative 100. So the mean y bar is still going to be calculated in the same way. So 8 plus 6 plus 7 plus 5 plus 3 plus 0 plus 9 plus 0 plus negative 100. Okay, and divide by 9. And so having changed that one value to something that is extreme, so that would be considered an outlier, right? It's an outlying value, and it is in the negative direction, so to the left of the rest of the data points. It shouldn't come as much of a surprise that our mean has now been affected pretty heavily or very strongly by that outlying value. And it actually goes down to negative 6.9 units now. And so this is something we want to observe, and what holds for most of our data sets that we're going to look at is that if you have skew or outliers, the mean is strongly affected by those and will be pulled in the direction of that skew or outlier. The median, on the other hand, so if we order our data to find the median, we're going to change out one of those zeros to the negative 100. Then we have 0, 0, 3, 5, 6, 7, 8, 9. Our middle remains the same. Having changed out the minimum value isn't making a difference to our median. So median equals 5 units. And so whenever our data sets have a strong skew or outliers, we'll rely on the median as our preferred measure of center. For this reason, right? We don't want to have the median get pulled by those extreme values, especially when those extreme values are not always what we're most interested in. We're more interested typically in what's happening, generally speaking, as opposed to those extremes. Okay, so more formally, mean versus the median. So if a distribution is skewed or has extreme outliers, the center is going to be taken as the median, since the mean is highly sensitive to skew and or outliers. If the distribution is symmetric, we'll usually take the mean to be the measure of center, since the mean and the median will be approximately equal. Okay, and this is true whether you have unimodal and symmetric like the picture shown, or you could have bimodal and symmetric, and that would still make the mean and the median approximately equal to one another. And so in general then, the mean is going to get pulled in the direction of skew or outliers. And this gives us some valuable information in determining what the picture of the distribution is going to look like just based off of the numbers for our mean and median, and vice versa. We can look at just a picture of the distribution and have some idea about the comparative values of the mean and the median. So in general, when we have right skewed data, the mean is going to be greater than the median, because again, when we look at kind of a blanket thrown over this picture with the right skew, our mean is going to get pulled in the direction of that skew, meaning it's going to be greater than the median. And likewise, when we have our left skew, and that was a smooth curve anyway, but you know what I mean, we're going to then have the mean pulled towards that lower value relative to the median. Okay, and so we can use that again both ways. We can either have the picture and give some indication of the mean versus the median, or we could just have the measures themselves of the mean and the median and be able to say something about the distribution's skewness or symmetry. Okay, so here's an example which is most likely to be true for the distribution of percent of time taking notes in class. All right, so this is the percent of time taking spent in class taking notes, this should say frequency, and we would want to have a title, of course, to get full credit. But the general idea, right, is we have this distribution. And so in terms of describing its shape, we would say this is unimodal. And we have our tail kind of trailing off to the left. So we have skewed left data and no apparent outlier. Only because we don't have singular or like just one or two values that seem to be significantly different than the rest of the data and the trend that it's taking. That doesn't actually mean that there are no outliers, and we'll probably find that were we to do calculations on this data, that we did in fact have outliers somewhere off in the tail, but we'll rely on numerical calculations rather than just our visual interpretation of the shape would say that there's no apparent outliers. So in terms of this description, what we're focused on, what you want to be careful with, is that we're only thinking about the skew or symmetry of the distribution. When we compare mean and median, it doesn't tell us anything about how many modes we have. It doesn't tell us necessarily about the outliers. What we focus on is just that skewness. And so in this case, since we are skewed left, that means that our mean is being pulled to the left relative to the median, relative to the median. So the mean is going to be less than the median. And so that will be C that we're looking for in that list. Okay. So now moving on to measures of spread, let's start by thinking about these two class score data sets. And so these are scores out of 100 that were in these two different classes. And what's funny about this is we're going to have these middle values. So 50 is both the median, and if we did the calculations, we'll find that the mean and the median are equal to 50. So mean and median equal 50, and therefore both of the classes have the same mean and median. But the data sets themselves, you can take a look at it, they're very different from one another. So we cannot rely solely on the mean and the median to give a summary of our data sets. We also want to include information about the spread of the data, how spread out from those mean and median values is our data. And we have three main measures of spread that we'll look at in this class. The first one is the range, and this one is actually not really looked at in this class at all because it, like the mean, but even more so, is highly susceptible to skew and outliers. The range is just simply the calculation of maximum value minus the minimum value. And so you can imagine right away that if we have an outlier, then that range is going to artificially express a lot of spread in our data, which may not actually be true for the bulk of it. So instead, what we rely on is the 5-number summary and specifically the IQR and the standard deviation. Now, the first one we're going to look at is the 5-number summary and the IQR. Now, this pairs with the median. So the median always pairs with the IQR as a measure of spread. So as soon as you see that there is, for instance, skew or outliers in our data set, we know we're going to want to use the median for our measure of center, and therefore we will also be using the IQR for our measure of spread. If we had more symmetric data, we would use the mean as our measure of center, and that would mean we would pair that with the standard deviation as our measure of spread. Okay, so the 5-number summary that we're going to use to calculate the IQR and also to make box plots down the road is going to consist of 5 numbers. The first one is the minimum. Then we're going to have the first quartile, or Q1 is usually how it's referred to. Then we're going to have the median as our third value, the third quartile, or Q3 is our next value, and then last but not least, the maximum value. Okay, so coming back through, so the minimum value, that is the smallest data value in our data set. Okay, Q1, or the first quartile, this is the median of the lower half of the data set. Okay, median, this is the middle data value. And third quartile, not surprisingly, this is the median of the upper half of the data set, and the maximum is the largest value in the data set. Okay, so that's the basics of those 5 numbers. Now, kind of coming back through this, we imagine then that we have this minimum value, right? Here's our minimum. And then we're going to have this next value, Q1, and then we'll have our median, and then we'll have Q3, our third quartile, and then we have the maximum. Okay, so this was the middle data value. Okay, so then we have half of our data kind of lying between the minimum and the median, so 50% lying below, and then between the median and the maximum, we have 50% lying between those. And then Q1 and Q3 are the medians of each of those upper and lower halves. So if we're splitting those 50% up, you'll start to notice then that there is 25% of our data in each of those regions we create with Q1 and Q3 between the min, max, and the median. So there's another 25% and 25%. So these quartiles in the 5-number summary in general are breaking our data set, our ordered data set, up into quarters. Okay, so a quarter of the data going between Q1 and the minimum, another quarter of our data between Q1 and the median, quarter between median and Q3, and so on. Okay, so given this breakdown of it, we can then see that the first quartile is also referred to as the 25th percentile, since 25% of the data lies below it. So again, going back to this picture, here's Q1, 25% of the data is going to lie below that. And for Q3, that is going to be the 75th percentile, since we have 75% of the data lying below it. 3 of the quarters lie below it. Now, a lot of people want to go, well, then the median must be the second quartile, and it kind of is, but we never really refer to it that way. You'll pretty much always hear the median referred to as the median and not Q2. Okay, but then this one we also know already is the 50th percentile. And if we had to put a percentile ranking on the minimum and the maximum, right, the minimum would be the 0th percentile and the maximum would be the 100th percentile. Okay, so that's the basics of it. Now, again, we want to make sure that we are seeing this as positional measures. So we need to make sure the data is ordered first. So data is ordered first whenever we're doing these calculations by hand, right? We're talking about the median, which was already positionally the measure of center. Therefore, all of these other values coming from the median are the same sort of practice of looking at percentile ranking, percents of values lying below. Then we also need to make sure that that's in reference to data that's been ordered already from smallest to largest. All right. So let's take a look at an example to see how this is done. We're going to look at the 5-number summary in IQR for the data set that we have seen before. So this is the one from the earlier example. We see that n is equal to 9. We're doing just positional value calculations. So we just want to put this in order first. So we'll have 0, 0, 0, 3, 5, 6, 5, 6, 7, 8, 9. We know then that 5 is our median. So median equals 5. And then we're going to try and identify the lower and upper halves of the data. Now, there are a number of different ways you could do this. Some texts and technology will repeat that middle value and place it into both the lower and upper halves. Other technology and methods include just ignoring that middle value and only looking at the numbers on either side of it. And that's actually the method we're going to use, and that'll stay consistent with our technology that we're using with GeoGebra. Again, if you use a calculator, if you use Excel, other technologies are going to handle this calculation for Q1 and Q3 differently depending on how they're figuring out the lower and upper halves. So this is our convention for the class, but that convention changes. You just want to be consistent with whatever method your particular text, instructor, or career field is using. So for us, again, this is going to be considered our lower half of the data. This is our upper half of the data. Upper half. We are ignoring the median from the halves, from the upper and lower halves. Okay, and so now we want to find the median of the lower half, and let's go with this. So the median of the lower half, in this case, we have an even number of data values in the lower half. So we're going to need to find the average or mean of the middle pair of values. So that means Q1 will be equal to the mean of that repeated pair. So I mean, it's going to be equal to 0. Most of the time you can just do this in your head. That will be the value of Q1. And then the median of the upper half, that's Q3. So again, we have 4 data values in our upper half. So we will take the average of the middle pair of values. So then Q3 will be equal to 7 plus 8 divided by 2, or 7.5. And these have units. The units are unspecified in our example, but they would take the same unit as the data set itself. So then altogether, this gives us our 5-number summary. So the 5-number summary is pretty much always listed in order as the min, Q1, median, Q3, maximum. Okay, and the minimum was 0. Q1 was also 0. The median is 5. Q3 is 7.5. And the maximum is 9. So that's our 5-number summary. And from there, we can find the IQR, which is the interquartile range. Interquartile range. So it's the middle quarters, so the middle 50%, and range is just talking about the width of the middle 50%. So in other words, this is the width of the middle 50% of the data. So it's very similar to the standard range, but what we've done is basically chopped off the lowermost 25%, the uppermost 25%, and focused our attention just on the middle 50%, where we're not going to have kind of that influence of the skew and outlying values. Okay, and so now the IQR is again Q3 minus Q1, width of the middle 50% of data. And so that's going to be 7.5 units minus 0 units, so 7.5, and those are just going to be the same units as our data would be again. Okay, and one more example by hand. Here is an even data set. We have 1, 2, 3, 4, 5, 6 values, so n equals 6. I'm going to make it a little bit bigger, but these are already in order, which is kind of handy. Okay, and so we're going to find the median, and that's going to be, the median is going to be the average of the middle pair of numbers. So the median is going to be equal to 6 plus 8 divided by 2, which is going to be 14 divided by 2. So it's going to be 7, and again, units. Now, when we have an even number of data values, the upper and lower halves are going to have half of the data values, literally. So divide by 2 to find the size of the upper and lower halves. There you go. Okay, so we're actually going to just go straight down the middle so that this is going to be our lower half. So it will include one of the values from that middle pair, and then the upper half will include the other value from the pair of the middle pair of values that we use to calculate the median. So technically speaking, just like with the odd case, we are ignoring the middle value in our upper and lower halves, because technically the middle value or the median of an even data set is going to be the average of the middle pair, so not one of the numbers themselves. So now we're going to go to our list. So our lower half includes 3 data values, which is half of the 6, and so our Q1 will be the median of that. So there's our median of the lower half, so Q1 is equal to 4. Median of the upper half is going to be Q3, which is equal to 10, and that's also going to be units, same as the data, the units of the data. So 5-number summary, we're going to have our min Q1, median Q3, maximum, and then we can read that off of our ordered list. For the minimum, Q1 is going to be 4, the median is 7, Q3 is going to be 10, and the maximum is 20. Okay, and then our IQR, interquartile range, is Q3 minus Q1, which is going to be 10 minus 4, or 6 units. And again, that is the width of the middle 50% of data values. And those are ordered, of course, when we're talking that way. Okay, so a quick overview of this 5-number summary: min, Q1, median, Q3, maximum. Those numbers are going to be automatically output in GeoGebra for us, so we won't have to do these calculations by hand basically ever on your assessments, but it is important to know where they're coming from. Also want to reiterate the fact that depending on your technology, you would get different values potentially for Q1 and Q3 than you do by hand or using GeoGebra. So just be aware and know that for this class, we are using the values from GeoGebra. That's what you're expected to use for your answers. And so that basically covers that. Now, the next step with this is to illustrate then our values that we get from the 5-number summary. And that's how we build box plots. And you've probably seen these before, box and whisker plots. And we're going to do a very brief overview of just the standard box plot. But what we'll really be doing in this class is drawing modified box plots. So box plots that take into consideration any outliers that we might have in the data. So here we go. We're going to display the 5-number summary using a box or box and whisker plot. And to do this, we're going to get the 5-number summary on an evenly spaced number 9, connect Q1 and Q3 to form an inner box, extend whiskers to the min and the max. All right, so the first step in doing this, here is our box and whisker plot. We're going to try and do this for the cups of coffee data that we had in the previous videos. So the first step is, since this is a 5-number summary that we're doing, we need to order the data. So this is a little bit larger data set. N is equal to 18. So what I'd usually recommend is go to the tens positions and kind of group those together and then organize them by those groups of 10. So I see that I have a 12 and only one value with the tens position of 1. Then I go to the 20s and I have a 20, 25, 25, 28. So those are all in order. Then I look at the 30s and I have a 30, 30, 35, and then I'll go to the 40s, and so I have a 43, 44, 45, 47, 48. Then I'll go to the 50s. I have a 53, 56, and then go to the 60s. I have a 60, 64, 67. And I'm writing fairly big, and so I knew ahead of time that I wouldn't be able to fit the 18 values with my handwriting across the page, so I broke it up. And to help me keep track, to make sure I was counting correctly, I did half of them on one line and then half on the other. So I should have 9 in each row so that it adds up to 18 altogether. Okay, this also is helpful because now I've split it in half. So this first line, this is my lower half, and this row is my upper half of the data, right? So that's going to help me find the Q1 and Q3 pretty easily. And then the median, because I know I have an even data set size, I know that my median will be the average of the middle pair of numbers. The middle pair of numbers is going to be the end value in this row and the first value in this row. All right, so my median, actually, I can actually just go through the whole thing. So the 5 number summary, we're going to have our minimum, which is just equal to 12, and this is cups of coffee. Then our Q1 median, Q3 maximum. So maximum is 67 cups of coffee. That one's nice and easy. Then the median is going to be the average of the middle pair. So that's the 43 plus 44 divided by 2. Or you can just kind of do that in your head to know that it's 43.5 cups. And then we're going to have Q1, which is going to be the median of the lower half. So my lower half has 9 data values, right? Actually, here we go. And so it's an odd number for the lower half, meaning that it's going to have a single value in the middle, and that's going to be the 28. And once I have kind of positionally broken down how many values on either side of it, so 1, 2, 3, 4, 1, 2, 3, 4 data values on either side, I can actually recognize that for my upper half, it's going to be in the same position. So both the upper and lower halves have the same number of data values, so the middle of that set is going to be in the same position. So then Q1 is going to be equal to the 28 cups, and Q3 will be equal to 53 cups. And I can then calculate the IQR, which is Q3 minus Q1, and that would be equal to 53 minus 28, which is 53 minus 28, 25 cups. So that'll be the width of our middle 50%. Now we want to create a box and whisker plot from this. This is not a modified box plot, just a box plot in general. So your first step is to make sure you create a number line, and your number line should extend from at least your minimum to the maximum and a little bit extra. So I probably want to make this go out from at least 10 up to about 70. So I'll go up by tens. So there's 10, 20, 30, 40, 50, 60, 70. Actually, I can probably get a little bigger than that. Let's see. Spread it out a wee bit. 20, 30, 40, 50, 60. There we go, 70. And these are cups of coffee. So don't forget to label your scale. Okay, and then we want to give this a title. So this is cups of coffee each month. Coffee each month, or last month, actually. Let's be a little more specific. So last month. So make sure to include that title. And notice again, this is a full number line. I haven't started drawing the actual box plot yet, but you want to make sure your number line is separate from the drawing itself. Right, you have a number line, and that's how you're going to place your values. So the next step is to make the box. So I usually do vertical lines to indicate the Q1, Q3, make a box, add the median. So 28 is Q1. So there's Q1. Q3 is 53. So somewhere in there, there's my box. The median was 43.5, so I'll put that as a vertical line inside. So this is the median. This is Q3. This is Q1. And then I'm going to add the minimum and maximum and whiskers out to those. So 12 cups is the minimum and 67 cups is the maximum. So somewhere like that. Okay. And again, a couple of things to recall here is that we have 25% of our data lying within each of the regions we've created in our box and whisker plot. So regardless of how long a whisker might be or how much larger a section of our box might be, it still contains approximately 25% of our data. And so we have a bad habit when we see this picture to imagine that data is spread out evenly across that region. And that's not always true. So that's the one deficit with this type of image for the data set. So here's 25%, this is 25%, this is 25%, and this is 25%. But we could have, say, a box and whisker plot that looked like this, and we could see like we may have an outlier. So we have like all this data right here and then a point over here. So there could be a whole bunch of blank area. So no data values here, right? And so you want to keep that in mind. The data isn't necessarily spread out evenly across those regions we create. Now, the other thing we want to recognize here is remember what the IQR is. The IQR is the width of the middle 50% of the data. So this is our middle 50% of the data. So this indicates the IQR is the width of the box equals width of the box. Okay, so that's the box plots. This basic form of it, pretty straightforward. Create a number line, give yourself a title, label the number line, make a box from Q1 to Q3, put the median where it exists inside of that, and then extend whiskers out to the minimum and the maximum. It is possible, as we saw in some of the other examples, to have if you have repeated values, you could see like we did, the minimum in Q1 being equal to one another. That's fine, treat it as just the vertical line of Q1. You could even have more of those values being equal. If your data set had all the same value repeated, then every one of those summary values would be equal. So don't get too thrown if you happen upon a situation where your, say, Q1 and your median were the same. That's okay. It just meant that you had a bunch of repeated values over that range of values. All right, so our next measure of center, the one that pairs with the mean, is the standard deviation. Okay, and so the standard deviation is used to describe the spread when we use the mean as our measure of center, and we're going to use the mean as the measure of center whenever we have data that is basically symmetric. Okay, the standard deviation tells us how far on average data values lie from the mean. Okay, and so the standard deviation is the give or take part of an estimate. So for example, in the statement, most students in the class are around 23 years old, give or take 3 years. The standard deviation is that 3 years, and the measure of the mean is 23 years. So that's where we would have that give or take. We don't want to give just a single estimate for quantitative data. You usually want to add in some wiggle room. Another way to express the standard deviation with the mean together in a meaningful way is to add and subtract the standard deviation from the mean to give a range of which most of our data is going to fall. So for example, most students in the class are between 20 and 26 years old. And so that's 20 is coming from the mean of 23 minus the 3 for the standard deviation. 26 is coming from the 23 as the mean plus 3 for the standard deviation. Okay, so the mean, or like the mean, the standard deviation is highly sensitive to skew and outliers. So it kind of sticks paired with the mean and used only in those situations where we don't have a lot of skew or outliers. So when our data set is approximately symmetric. The sample standard deviation is given the label S, we've seen this one before, and is computed as the square root of the sum of the squared differences divided by the sample size minus 1, or this big old beast of a formula. Now the stuff that we have inside the square root, this part here, that's referred to as the variance. And since it's inside the square root and we take the square root of that to get to S, it's given the symbol S squared. Okay, and the population standard deviation we already know about, and that's given the symbol sigma to make it different from the standard deviation. And its calculation is actually different from the calculation for the sample standard deviation. So if we're doing sigma, that difference is what we divide by. So there's still the sum of all our differences of our data value from the mean. We square those, but we divide by uppercase N, the size of the population, as opposed to N minus 1. And the N minus 1 happens to do with things called the degrees of freedom, and so we don't need to worry about that in this class. It's not a big deal. It's not going to have any bearing on what you're tested on, but just know that those calculations are different. We treat the sample standard deviation calculation differently than we do the population standard deviation. So those symbols become that much more important, and what you select in your technology for the answer to a question about standard deviation matters as well. All right, so here is your basically one and only by hand calculation, because the standard deviation calculation is kind of ghastly, right? It's a big old calculation. So we're going to find the standard deviation for this data set of 4 values, and just that is enough. Okay, so the first thing we want to notice is that we're needing to do a difference of each data value from the mean. That's that subtraction part of our formula, and square it. So I need to know the mean of the data set first. So I'm going to find the mean. So y bar is going to be that 5 plus 7 plus 7 plus 10 divided by number of data values is 4, and so that's going to come to 7.3. And again, we don't have units here specified, so I'll just use the term units. All right, so now I'm going to calculate the variance first. Whenever people do these calculations by hand, it usually happens that people forget to do the standard deviation. So it's easiest just to do the inside and then take the square root of that result so it's not lost somewhere in the process. So we have s squared, sorry, my dog just came to visit. The variance is going to be equal to the sum of each of the data values minus the mean squared. So we're going to take each of our data values in this order. So 5 comes first, minus the standard deviation of 7.3 squared, plus the next data value, 7 minus the mean squared, plus the next data value, 7 minus 7.3 squared, plus 10 minus 7.3 squared, divided by n minus 1. So there are 4 data values, minus 1, that'll be 3. All right, so that is a big old calculation. Now you want to try and do this all at once in your calculator. Don't do the partial values and the squaring of it. We're only going to be doing very, very small data sets if you are doing this by hand, in which case it'll be a little more manageable on your screen. And this should get us to 4.25. And this is the standard, or this is the variance, not the standard deviation yet. So our units are actually squared at this point because we took our values and we squared them all, right? So that means our units got squared in that process. Now we can get to our standard deviation S with the square root of that. So the square root of 4.25 is going to give us our actual standard deviation, which is 2.06. We're back to units again, or we can take this to just one decimal place, 2.1 units. Okay, so a couple of extra comments here. First of all, I'm taking my variance to 2 decimal places. And that's because we don't want to over round ahead of time. We want our final standard deviation calculation to go to 1 decimal place. So any intermediate steps you want to take to more than that number of decimal places. So 2 or 3 is usually where we want to go. You also want to notice that the units are what are squared. We already did the squaring of the number. So it's not the number squared, just the units are squared. So just units squared. Okay, everywhere else we already had the units done. And then we're going to go back to 1 decimal place for standard deviation as our final value that we're looking to get. And then since we took the square root, we took the square root of those squared units as well. So that takes us back to the units of the data, back to the units of the data set. Okay. And then last but not least, we'll want to think about this a little bit more conceptually. So which set has the larger standard deviation? Okay, so for us, when we're looking at this, you want to kind of recognize off the bat that we have basically the same mean. So the mean on both of these sets are equal to 7. Okay. And then when we think about what is the mean, well, the mean represents how far on average data values lie from the mean. Okay, so our calculation of that was the square root of the sum of y minus y bar squared divided by n minus 1. Sample sizes are the same, so that's not going to have any real bearing overall on the comparison of the standard deviation. That part's the same, right? And square root of a bigger number is still going to be a bigger number. So we don't need to worry about the square root in this calculation. So what becomes important, and the same as the square, right? That squaring doesn't much matter. What matters is the sum of those, or looking at those differences. When you have a bigger difference between a value and the mean, that's going to lead to a larger standard deviation overall, right? And so we want to compare their differences. So the difference between 7 and the mean of 7 is a 0 difference, right? And there's a 0 difference here as well. When we go to the 4, that is a difference of 3. Right, so we've got a minus 3 over there, and then we also have a difference of 3 over here. So what we're looking at then is a difference of overall that's going to incorporate that negative 3 and the positive 3. Now when we come over here, we've got a difference of 1 on both of these guys, and then we have that same difference of 3 over here, right? So the minus and plus. And so in terms of the calculation, we have similar values here, right? Those remain the same, but instead of having a 0 difference between our mean and data values in this first set, we now have a difference of 1 from that mean in this other data set. So that's going to make the standard deviation larger, makes the standard deviation larger, to have those data values with differences from the mean that are bigger than the other set. So the set here, so this set has a larger standard deviation. Okay, just by taking a look at it that way. Okay, and that should cover it for now, and we'll go over another video how to do the calculations of the mean and the median, standard deviation, 5-number summary in GeoGebra.